pause all the streams that have started. I'm gonna introduce a thing called the sneeze test. Can you hear me sneeze? Hi, Alvaro. Yeah, it's Thursday, Summersoft. We're a day early. Hi, Mark. Okay, I can close this. I should have it here. Oh, let me pause restream. I don't get why streaming services insist that you watch your stream from them. Like, my computer's busy doing enough video stuff. Why would I want 3 more streams coming in? Mark says sneezing loud and clear. Good, sorry. Maybe I should have a button to actually mute when I sneeze. There is the audio in sync? Because it kind of looks like it's not from OBS. I know we had trouble with that last time, maybe. I don't know what I can do. YouTube is not receiving enough video to maintain smooth streaming. So YouTube's warning me that I'm not super happy. OBS looks like it's behind, but it's not the end of the world. I wonder if the hover cam is it possible that that's throwing it off? A little out of sync on Twitch and also on YouTube. Crazy frame drop rate. Wait, let me... if I disappear, it's because I turned Wi-Fi off. So I'm going to turn Wi-Fi off. Maybe that will help. Hopefully you can still... Kilobytes per second dropped. Why is it so low? Oh, you're seeing a black screen. That may be why. Is that any better? Any better, any better, any better? Did that help? I don't know. All right, we're on Twitch and YouTube. What we may have to do is just do what we did last time. And I mean, I could try to play with the settings. Is my audio... I think that there are delay settings. Which direction do I have to change the delay? Do I have to delay my audio more, or do I have to delay my video more? Properties. Advanced audio properties. Frame rate okay, audio out of sync. Does that mean the audio's too slow? Mic aux. Audio monitoring off. Any idea how much delay it needs? 10 milliseconds might be a lot. All right. Is that any better? I'm not going to fuss with this too much. I set the audio delay to 10 milliseconds, so we'll see. I'm not liking this camera. I think... I know it could be my laptop, actually, because it's hot in here today. I wonder if it's actually the temperature that prevents the CPU from kicking up as high as it could when it's cool in here. That would be fascinating, actually. If my performance... I mean, it makes sense, right? If my laptop can't cool, it can't go as fast. All right, well, I'll have to play around with that. I definitely can see that, like, even the screen back to me is a little slow. Hundreds of milliseconds. All right, well, I can try that. But tuning that's going to be a pain. I'm sorry. I think what we're going to have to do is just... That's so weird. I can do like 200 milliseconds. I assume that it takes effect pretty quickly, but I don't actually know. Let me know if that changes it at all. I don't know. I think it probably is that. I mean, I could see if there's an update. Check for updates. No. Yeah, it might be just because it's hot in here and the computer can't go as fast. So I think what we'll do is we'll just do what we did last time and move my screen so it's less annoying. All right, so I'm down in the corner now. I'm still delayed, I think, a little bit, but it's okay. YouTube is giving me... Is YouTube buffering? Can anybody tell me that? It's a bit better, I think. That's good. I set it to 200 milliseconds like Johnny was suggesting. But I don't know, like, it just started happening, and maybe I updated macOS since then. But I don't think OBS changed, so I don't really know how to root cause it. And this camera, the more I use it, the less I'm excited about it, too. So, yeah, I think we're just going to roll with it. It's already 5 minutes into the streaming, so we've hopefully collected some folks, and... we'll get rolling. I'll be down in the corner. Sorry if it bothers you. It would bother me. But yeah. So let me do my screen and then we'll see. Hello everyone. My name is Scott and I work for Adafruit on CircuitPython. Oh, it's much better. Great. I work on CircuitPython for Adafruit. Adafruit is a company based out of New York, and they do open source hardware and software. I'm a freelancer for them, and I'd encourage everybody to go to adafruit.com and purchase some hardware from Adafruit because it funds the software work that I do that's all open source, and a lot of hardware and software outside of just what I do as well. So this is a deep dive stream. They tend to last about 2 hours. That's my goal today. I don't have anything afterwards except I'm going to go for a walk outside because it's beautiful. If you're keeping track, it's definitely an ice water day. Hopefully I will not spill it on my laptop or on my keyboard. I do these deep dives typically Fridays at 2 p.m. Pacific, but tomorrow is Juneteenth, which is... a long celebrated day of the freeing of slaves in Texas after the U.S. Civil War. If you're not familiar, if you're from Europe, I know we have some Europeans, or maybe you're outside of the U.S. Basically, in the 1860s, there was a war between different states within the United States. One of the contentions or the conflicts was the legality of slavery, and as a consequence of one side winning, they mandated that all the slaves be freed in the other side, the Confederacy. And Juneteenth is June 19th. It is the day that the Union imposed that slaves be freed in Texas, which was kind of like a far western state in terms of the Civil War. So it's not something that I've grown up recognizing and celebrating. I think I may have learned it in school, but a lot of the communities that I've grown up in had very few African Americans. So I'm trying to be better. I'm more aware of it. So that's the reason that we got our days shuffled. This is the same time that I streamed when we took Memorial Day off, which is another U.S. holiday. So I thought it was fitting to do that today as well. So that's the deal. That's why it changed. And thank you to everybody who was flexible with that. But typically I'm 2 p.m. on Fridays. As always, if you have questions about stuff, drop them in the chat. And I'll respond to them. Sorry for the audio and video mismatch. It's just something, I don't know why. Other housekeeping that I normally do. The best place to chat, I think, is the Adafruit Discord server, which we're in all week. I'm in, and a lot of other folks are in. You can go to adafru.it/discord to join that group, and we hang out during the live stream in the live broadcast chat channel. So hope to see you there and in the Discord more generally. I did a stream last week with Nina. All right, YouTube looks like it's happy again, which is good. I did a stream last week with Nina on Python T on Friday. I didn't talk much CircuitPython at all, actually. I did a lot of talking about the election cal stuff, which I'm not going to talk too much about today. If you have questions about it, I'm happy to answer, but basically looking forward to doing some more work on that this weekend. Heads up about the cat. Those of you who watched before, one of my two cats, Spook, likes to sleep in the window here, and he is epileptic, so he occasionally does have seizures. If he has a seizure, I'll just pause or mute my mic, keep an eye on him, make sure he's okay, and then once he's done about no more than 5 minutes, then I'll just hop back on the stream. Probably let him out because he likes to go downstairs afterwards. That's the deal with the cat. So the plan today, last week on Friday, it was kind of like a shortened stream. It was basically just an overview. So what these streams tend to be is like an overview of the work that I've done since our previous stream. And then some deep dive into some technical work that I've been working on. So we covered a lot of different things last week, but didn't really do much deep diving. My plan today is to start with an overview of what I've done, which is mostly SPI and UF2 stuff, and then also and then dig into the SPI stuff, because I've basically written a lot of code and I haven't tried to compile it or test it yet. So I thought that would be kind of interesting, and there's some interesting topics to talk about there. Before I do that, let me first talk about the UF2 stuff. So last week on kind of the overview show, I had shown, sorry, this is in the corner, but my poor laptop is like, it's a MacBook Pro, but I think it's mainly a thermal issue, like just not being able to handle a lot of streams of video. I was actually thinking about using my gaming machine. I may try switching, actually, because it's probably got a lot better cooling. But I showed this last week on just the overview show, and I guess that comment was because I'm not running the overhead, but it's probably blurry. Sorry, but I have this little thing here. It's an RC circuit, which means it's just a resistor and a capacitor. I picked, and as I was talking about last week, its use is as a 1-bit memory. Basically, a lot of our UF2 bootloaders, if you hit reset, you double tap it, it will stay in the bootloader rather than loading the code that's loaded after it, such as an Arduino sketch or CircuitPython. So I'll just show this off, actually. But there's been changes to TAC's UF2 repo to support the double tap. So if I just plug this in, the color does change. And let me pull this up. And we'll see if it works. It actually didn't show anything. I don't know what's on here. It should show CircuitPython, but maybe it's unhappy with me. It's just a unhappy day for my computer, I guess. So let's just see if the bootloader shows up. So I'll just hit the reset button here. I did this yesterday on Show and Tell, and it worked just fine. And it's literally just been sitting on my desk. So yeah, it's showing red right now, which means the bootloader is running and it doesn't know the state of the USB. So something is, my laptop must be unhappy with the device for some reason. So I just moved ports on my hub. We'll see if that, but this is green now. So I'll click it and we'll see if we get CircuitPy. Summersoft says, yeah, it worked 5 minutes ago, the summary of my development experience. Yeah, that's the other theme of this whole live stream is like, oh, it worked yesterday, but now it doesn't work. And I don't know why. It's still not working. I switched ports. I do have other USB cables. Just take my word for it. I was... Yeah. The double tap works. It's just the USB side. So it's if you double tap, it stays with a thing lit up. It's meant to really make it really easy to get into the bootloader, and it's also meant that it's by having this on ESP, even though it's been kind of tricky and it requires extra parts, it means that the user experience is going to be the same. Which I was half joking, I think maybe last week, but I feel like even as I did like I don't know like 3 hours of PR reviews earlier today, along with email and stuff. Like I feel like more and more of my job is simply like pushing people to make things the same as other things. Um, so yeah, like TAC was asking me, what should the LED patterns be? And I said, they should be the same as the other bootloader. Uh, so yeah, it's important to have consistency, and sometimes we forget about that. All right, so I'm not going to worry about that. If we'll, oh, you know what? You know what the reason is? I'm plugging into the wrong USB port. So this USB port is the serial port for the ESP, not the native one. That's what I get for making a device that has 2 USB ports on it. Of course, I say that. Oh, there we go. And it does show up. So if you look on the screen, you can see a CircuitPy drive, and you should eject it. Actually, I can eject it. So I'll eject it. And then if I hit reset twice, it's not a super fast reset. There's actually like a time window where you could be too quick. But now we see a Sala 1R boot folder. So that's the like fake fat file system that is presented by the UF2 file system. So yeah, it works if you plug into the right USB port. Great. So that's the first thing. The other thing I wanted to talk about, actually, I just wanted to get some feedback on because I just thought of it. We were talking a lot about maybe it was 2 weeks ago now when I did the big discussion of like buses and bus terminology. We had this big discussion about like replacing the terms master and slave with something more descriptive. And we have this ongoing PR in CircuitPython that Jeff started, which is awesome, that's renaming stuff to get away from the term slave in particular, master and slave. And I just had this idea. The challenge with SPI in particular is that 2 of the pins are called MOSI and MISO, which are acronyms. Master out, slave in, and master in, slave out. The benefit of those pin names is that like you connect the same name across and it works just fine, because it's kind of like the term includes the like both perspectives of it. Now, I just had this idea when I was thinking about it of like, what if we think of the names of the wires separately from the names of the devices themselves? And I thought of this idea of calling that, like renaming them master output shared input and master input shared output. And the idea there is that like your MOSI line goes from your, did I say master? Main output, main input. So it goes from like your host, right? And then it runs to all of the devices on that bus, right? So that's why it would make sense as a main output, but a shared input to all of the devices. So if you have thoughts on that, I was just thinking about that, and I kind of like that because the lines are shared amongst devices, which I think is cool. What do you think? I wonder how our delay is. Are we not going at all? Everything looks good, but chat is quiet. Take a water break here. Summersoft is typing. Oh, I have hot corners on the bottom. But yeah, I thought that was a good idea of using shared for S. Anecdata says shared is much better, greater than, significantly greater than secondary. Mm-hmm. Yeah, so kind of like the previous front runner on this discussion was main and secondary, and main what, secondary what. But it was clear from Hierophect and Foamy Guy that like we really like the terms. So I think that keeping those acronyms would be best, ideally. But nobody's replied to me on this PR. That's why I was like, it might creep in the thought that the select line isn't necessary. Yeah. Better than secondary. Yeah, I think I like shared because it brings up in my mind the idea of like, how do I know, since it's shared, how do the things know when it's their turn? And then you can clearly say that like chip select should then be kind of like not slave select, device select, right? So if you have a host that is your main input and you have shared outputs into it, like you have to have a discussion then about like how you share, and that's what the select lines do. All right, well, cool. I just wanted to pitch that because I thought of it and I like that idea. Okay, so let's see what's next. I talked about UF2. Yeah, the bus line itself is shared. Thumbs up. Yep. Yeah, that's my thinking, is that the bus line itself is shared. Which is, it's kind of interesting thinking about the way that the lines are shared in I2C as well. But like they have different method for deciding whose turn it is. Okay. I just wanted to cover that. And here's tax UF2 repo with instructions on that. And okay, let's dive deep, I guess. So on Friday, I did UArt on Tuesday, and then I was kind of procrastinating on SPI. And I think I talked about this conundrum with SPI that the ESP IDF. Oh yeah, I remember this because Arturo was like, "Oh, I've got it working," kind of. So I looked at what Arturo did, and it didn't handle the things that I thought were the hardest part about adding SPI support, and that is that I2C, when you're sharing the bus, you basically have to pick a speed that works for all of the devices. And the reason you have to do that is because that speed dictates the address transmission rate. And every device on the I2C bus has to be able to listen for the address to know whether it's their turn or not. That is not the case. This is kind of a nice segue from what Summersoft was talking about too. In SPI, that's not the case because each device has a separate chip select line that dictates when it should listen to the bus or not. And typically the speed of that is pretty slow because it's only changed like once per transaction, which means that you can actually have different settings for the shared lines based on the different devices. So I was looking through. Actually, maybe I should do that today too. A secret thing that I was also thinking about. So I was going through these, not this API, but if I just pull it up here, I was just like looking through the SPI host stuff. Like that's what gets me is like we're still using master and slave terminology, and then the first thing that like when we actually talk about it, we use host and device more. So why not just do And then like it's called data transmission from a device to host. Like we could easily replace this as in main input, shared output. And then you could say data transmission from any one of the devices to the host. I think it's a good idea. Obviously. Obviously. Yeah. Hi, Unexpected Maker. Thanks for popping in. I know 2 hours is a long time, and it's your morning, and it's later. Thanks for saying hi. We're talking SPI APIs. So the thing I was talking about last week was that this driver, the driver level API for the ESP IDF, is almost all done at the device level. So the only two, let me scroll down to it. Yeah, so the only two things that you can do at the bus level are initialize it and free it. But if you look at all of the transaction stuff, so at the bus level, this is where we pick all the pins, and I'll go over what my changes are or what my current implementation is as well. So we pick all the pins and we set up some flags about like how we're going to use it. And YouTube's unhappy again. What does Restream say? Restream looks okay. Yeah. Not a whole lot I could do. Sorry if it's choppy on YouTube. Hopefully it's not choppy on Twitch as well. It's actually kind of interesting because Phil and Lamore have been having a bit of trouble from their end as well. I wonder if it's internet weather or whether it's actually a restream. Yeah, if for those of you who watched Ask an Engineer last night, if this stream feels like the stream last night, which I was watching, let me know. I'm curious about that. I wonder if it is Restream that's having some issues. Yeah, because it was choppy last night for me. It was actually choppy the last couple nights. But it shouldn't. The streaming shouldn't be an issue from my side, because I'm on fiber and fiber should be able to upload like 800 megabits a second. So yeah, it shouldn't be too bad. Anyway, yeah. So the thing with the challenge that I spotted when I was starting to look at the SPI host APIs is that if you actually wanted to do any transactions, you had to do it at the device level. Mark says, last night the StreamYard audio was out of sync for me watching them talk when I was in the lobby. Not much, but just perceptible. Yeah, I don't think I noticed that. I kind of assumed it was their internet connection, but I don't know. It could be my laptop, like I was saying. Maybe I'll try to set something up on my desktop and maybe try doing some development from Linux instead. I don't know. Anyway, so this is the challenge, is that, you know, and for the same reasons that we in CircuitPython have this device model for all our driver level stuff, right? So we have kind of like, if we're talking about our driver stack in CircuitPython, we have the native bus IO API, which is what we're implementing. And then right on top of that, we have Python library bus device, which is the thing that manages the chip select line and also reconfigures the SPI bus for every transaction. So like I was saying, or getting to, is that because the way that the devices on the bus decide to share, the speed of the bus can, and actually like the configuration of the bus itself can change from device to device. And so like Espressif had made a really good design decision, if they're the top level API, that like they'll manage that reconfiguration and stuff. Unfortunately, like that doesn't work because we do that in Python land. We don't do that in C land. So I've actually spent a lot of time digging into what I think are the weeds of the ESP IDF, because basically what I'm doing is I'm trying to use the highest level I can where I can, uh, largely because I want to make sure and kind of like coexist with the ESP IDF, because the more that I can successfully coexist with the IDF, like the less problems we'll have as we add other things. Um, which is another discussion that we should get into in just a little bit. But I think what I'll do is I'll run down the code as I have it now. And I haven't compiled it and I haven't tested it yet. So this is like very early, kind of in the process. So like if I had to say what my process was, and maybe I've shown this on the stream before, but I like to, in this case, I make, the empty file. You saw this, like all of the APIs, and just stub them out, delete all the stuff, or comment out all the existing implementation, and then like start adding it. And kind of the way that I do it is like I'm basically like side by side looking in the IDF code. And in fact, I think I might have, yeah, I've actually got a second window open up here, which I'm not going to be able to do on the stream, because the stream window is just like a portion of my monitor. But I actually have two different Sublime windows open, and I've been having them side by side, where like on the left hand side is my implementation of the bus IO SPI stuff. On the right hand side is all of the ESP files that are related to it. And so let's just run down where I'm at. And this is the wrong file. So here's the file. So that's I2C, and we've gone over that, so I'm not going to go over it today. But let me just walk through this. Does that sound like a plan? Any questions? It's like we have 16 folks watching. If you do watch it later, you can put a comment on YouTube and maybe I'll see it. But the better thing is to go to the Discord and ask me directly, because I don't necessarily look at the comments that often. I kind of only looked at them the next week when I grabbed the YouTube link. And so like last week's doesn't have any comments. It had like 1,200 views, but who knows like how far they get through the hour-long video, or in this case, 2. Although it's only a half an hour in, so I don't know, maybe I won't make it 2 hours. Depends on my voice and how hot it is in here, which is kind of hot. All right, let's go over this. So one of the first things that we do is, or one of the things that we have to do in a driver is we have to keep track of never reset. Never reset is something that we use for basically exempting certain hardware peripherals from being reset. So in CircuitPython, we like to be very strict in that, like when your code starts up, any of the hardware that you use is reset and kind of in the default state. That's the same state every time your code runs. But SPI is a bit weird in that it can be used for displays. And when I was thinking about how to implement displays, I wanted displays to actually live outside of when code.py is running, so that like once you've instantiated it and it's working, like we actually want to use that for CircuitPython things. So if you've ever used CircuitPython with a display and you get an exception, like we'll pop up the terminal or the serial output on the display that you have, including like an e-ink. And in order to do that, we've basically got to keep track of like the things that we don't want to reset. So there's this concept internally of never reset. I just have a Boolean array that I keep track of. And the thing that gets called after Python code is done to reset is this thing called SPI reset. There's a lot of different reset implementations, but basically we're going through, there are 3 SPI hosts, or 3 SPI peripherals in the ESP32-S2. There's 1, 2, and 3. And there might be 0. So it is actually interesting, and I asked Ivan about this, that this is going to pop up some reading about prison reform that I want to do. Let me open. Oh, you know, it's not even in preview. I have it in Firefox. In this window. Lots of windows. Like, I'm trying to keep kind of the state of both. Hey, TwitchBot. It is 33 minutes late, always, isn't it? TwitchBot just posted on Discord that I'm streaming. Thank you, TwitchBot. Okay, so if we look in, this is the data sheet for the ESP32-S2, and I can make the window a little bigger, and this also a little smaller. So this is the data sheet, and some vendors do this and some don't, where they have like a data sheet that doesn't include all the register descriptions and like the deep dive-y sorts of stuff, and then they have a technical reference manual or reference manual. IO MUX does this, but Atmel doesn't, so they have just a like 1,000-page data sheet instead. But if we look here, we're talking SPI. We can see that, like, okay, I was wrong. The ESP32-S2 features 4 SPI interfaces, 0, 1, 2, and 3, but 0 and 1 can only be configured to operate in memory mode. And then 2 can be general purpose, and 3 can be general purpose. Right, so the first thing that we have to worry about, or I guess we're talking about reset still. So in this case, we just have two possible SPI peripherals that we're going to use, 2 and 3. And we can see that kind of here, that like these are memory mode and then these are general purpose. Although 2 is weird in that it can kind of do other things as well. It can do memory as well. So when it comes to resetting, we have to do this for loop, which is here. So we do from SPI 2 to the number of SPI devices in the SOC. That's kind of known as the host ID. And we just iterate. If it is marked as never reset, we continue. Otherwise, we call SPI bus free, which is the ESP IDF high level bus like allocation and free API, and it is actually doing memory allocations in that case. So yeah, that's what we're calling here. Next up, let's go back to our code. So one thing that I did is one of the main things that we have to decide when it comes to CircuitPython is that the way that we do it is you tell us, hey, I want SPI on these pins, and we pick which of the two, in this case, SPI 2 or SPI 3, we should use to actually make that happen. And so one thing I needed is that, did we talk about the MUX stuff? But basically, there's two ways that the SPI peripherals can be connected to the outside world. One of the ways is through the IO MUX, which is like a very near the pin MUX, but it's very inflexible. And then there's also the GPIO MUX, which then gets routed through the IO MUX. And the GPIO MUX is much more flexible in that like any incoming pin to the GPIO MUX can go to any outgoing pin, which is awesome. It makes a lot of this code that I'm about to show you much simpler. Because in like a SAMD, there's like 2 or 3 spots that for any given SPI it could end up. So this is just a function that I took straight out of the IDF because it's static in the IDF, and I'm just doing it static here as well, which basically means like nobody from the outside world can use it. So I just copied it because it's Apache 2, and that's okay. I just preserved the license, which is part of the license. So this, all it's doing is it's given a SPI bus configuration and a host ID. It's telling us whether it's able to use the IO MUX directly or whether it has to go through the GPIO MUX. And that matters because the speed that you can run the bus at varies from, I think the GPIO one caps out at 40 megahertz, whereas if you're going only through the IO MUX or directly through the IO MUX, you can do 80 megahertz. And so that's double the bit rate. And if you're doing something like filling a display of bits, you're twice as fast as twice as fast. Um, so let's see. So SPI bus free is just a helper to check if the bus is free. And we do that by calling this. There's this function called get bus attribute or whatever. And it's just I'm just seeing if it's null or not, because I looked at the implementation, and the way the IDF keeps track of like extra helper information about the buses is it just allocates it internally and stores the pointer internally, which we'll see is a little bit tricky. So here we just check, or we're setting the ESP IDS version of the bus config, where we pick all the different, put all the pin numbers in, and we basically translate like null pointers to -1s. And we say we're going to be the master, and we have a clock. And then, like, depending on MOSI and MISO, we have bus flags for those as well. And now here's the place where we have to decide which SPI host to use. And as it's written right now, the idea is that if you give it the 4 pins or the 3 pins that the SPI2 host so SPI2 can connect directly to the IO MUX, but SPI3 cannot. So basically, if you are asking for the specific pins that SPI2 is on, we'll give you SPI2. Otherwise, we'll give you SPI3. However, if SPI3 is already busy, we should give you SPI2. Now, there's a wrinkle in this logic that maybe I'll get to. I don't know when I'm going to get to it, but we'll talk about. I'm going to stand up. It's so hot in here. So, okay, you can see my face still. So that's what this is doing, is we're basically going to pick SPI3 unless you ask for the specific pins that SPI2 is on. I think that's a reasonable thing to do, although we'll talk about a reason later that may not be the best thing to do. So we're calling that top level initialize thing. It is doing memory allocations internally, so we check to make sure that it didn't fail. If it does fail, we'll return a memory error. And I think I want to factor this out because if you see, I put it in 3 spots. We're going to assume that invalid args are just because of the pins, because we're just passing those in. I think the only way that that'll actually happen is that if we use pin 46, which is input only, as an output, then that should fail. We're not checking it ourselves. And then this is where it gets a little trickier in that I don't want to register a device. And this is what Arturo just registered a device with a 10 megahertz or whatever. But I want it to be a bit more flexible, and I want to make sure that we can hit the top speeds ideally as well. So here's where I started to kind of dig under the hood of how the device stuff actually works. So, one of the challenges, and this goes back to that first live stream we did about using an OS, and the OS itself is concurrent. So at any point we could get interrupted and something else could run. So the ESP IDF is really good about having locks. Sorry, I have a thing that I'm standing on. That's why I'm dancing around a little bit. The IDF is really good about tracking locks and stuff to make sure that you like don't change something, get interrupted, something else changes it, and then you go back to where you were changing it. Can cause all sorts of problems. And so what I'm trying to do here is like you reuse the kind of same thing that the SPI driver does, but kind of for myself, of having a kind of device level lock. And the CircuitPython API does have a lock and unlock for a similar reason, where with CircuitPython, we could potentially internally want to use a SPI bus that is also being used by user code. And so we want a lock that way as well. So locking is good. It's just complicated. We check for in-memory error because it's doing an allocation again. And then we also, the SPI driver from the ESP IDF does kind of keeps track of where we are in the transaction. And when it's done, an interrupt happens. It keeps track of some queues and pushes stuff on the queue, which like causes FreeRTOS to like kind of start back up the thing that started the transaction. This is the thing that I don't think I've finished. I actually need to finish this before we get to the point where we try to compile it. Or we could try to compile it and chase down bugs, but I don't know. We're going to have this function. That's going to be one of the errors. The thing I was thinking is I would just actually make a second lock where like when a transaction starts, you like take the lock and then you wait for an interrupt to unlock it, something like that. So I have to do that. We'll see, but the internals of the IDF driver do this interrupt allocation. So this is a point where I should talk about memory management, and this I think is also it's kind of a hybrid. Somerset says, distraction alert. Have you had ligatures on this whole time? I just noticed them. Yeah, I've had them for a while actually. So, I've actually had them a while. I think I've had them all the times I've streamed. But for those of you who don't know, I think this is the right way to say it, but ligatures are combination of characters. So if you have two characters in a row, you may actually like have a different thing render. So one place you can see it is this arrow here, where this arrow is actually like a dash and then a greater than. It's okay, just remind me where it was. But if I delete that, now I get kind of like one thing. And then the other place that you can see it is the not equals. So here is like a double equals with a slash through it. But if I put a space in the middle, we'll see that it's actually an exclamation point and a single equals. So yeah, I think I did that at the same time as I did the terminal stuff with the power line, like fancy like terminal things here. I think that I'm using the same font. Yeah, I'm using the same font, so we'll do the same thing. I've gotten used to it. It does take a little time, but as long like you can still edit it in the same way. So, yeah, that's the ligatures detour. And I don't know how to. It's been so long since I did the settings that I don't know. Yeah, so I'm using this Furacode Nerd font is the font that I'm using. So it's all font mechanics that do that. It's not like specific to Sublime. Okay, enough of that detour. Let's talk memory. So there's two weird things that we need to think about. One weird thing is that when we first started talking ESP32, there was build system, FreeRTOS, and the memory hierarchy. And this is kind of the last two where the memory hierarchy impacts DMA. So there is, let's pull up the data sheet. Let's kick it over to the datasheet. If we look at internal memory here, it breaks down like all the different memory regions. And the ones I actually only care about are this 320 kilobytes of on-chip SRAM. And it also importantly says it's for data and instructions. And then it also says that you can have external flash and RAM. And this tells you what numbers they go into. There's caches in front of this is kind of important. So embedded memory gets access directly, and then DMA also has access to embedded memory, but the cache for external memory, there's a cache there. And the reason that is because external memory is going to be slower to access because for a couple reasons. One is that your wires are longer, which means that you can not necessarily clock them as fast. And then also you may have fewer wires. So you may only be able to load like 8 bits at a time rather than loading like 32 or even 64 bits at a time. So external memory tends to be slower. And so there's caches in front of it. But caches are like a limited set of the memory. So basically it's slower. It's slower if you're accessing a lot of different regions. And then the other thing to think about is DMA. So have we talked about DMA? It's now the time to... I really should have like an index into all these deep dives where I talk about different topics. So DMA stands for Direct Memory Access. And it's super, super helpful because it is a peripheral, just like there's a SPI peripheral, but it has access to memory. And it's really helpful for moving data around without the CPU having to do it, right? So the CPU, the central processing unit, is this generic machine for doing logic, right? So all of the assembly instructions could be like, oh, if this, do that, do this sort of math, that sort of math. Or it can also just like load stuff from memory and write stuff to memory. So at the very basics, if you want to move something from here, like from RAM to a peripheral, like SPI, like the CPU can be a part of that, where it just like in a control loop, it's just saying load 32 bits, write 32 bits, load 32 bits, write 32 bits. But if you have a lot of bits, that's kind of a waste, right? Because the CPU can do more thoughtful things, I guess. Like it can do conditionals and stuff. Not just like a loop is a conditional, but it's still not that impressive. Right. It's not necessarily doing like running your CircuitPython code. So DMA is a separate peripheral that happens to be on, I think, all of the chips that we run on, but it's basically, some machinery like SPI machinery that has access to memory that you can say copy from this address to this address, this many bits, and then it will just do that as it can, so that the CPU can then go off and do something else. Now, one thing to think about, and this is a deep dive, that's why we're diving deep. And one thing that's super interesting and fascinating with these systems is that, and I think we talked about that there's actually 2 memory buses in the ESP32 SPI, but basically the memory buses are also a resource. And so if you were trying to have DMA like load and store a bunch of stuff at the same time that the CPU is loading stuff and storing stuff to the same place, you might actually like not be any faster because those 2 things have to share the memory, like physical lines to the memory, potentially. So it's interesting because I think a lot of people tend to think of performance or bottlenecks only in terms of CPU time. But there's a lot more different resources that you can think about in a computer. And memory buses are one of those things. So let's talk a little bit more about the way that the DMA works. And I think it might be in the other in the technical reference manual, not in the data sheet. So here it just has like DMA boxes, and I don't see a subtitle here for DMA. So let's switch over. But I want to point something out, and this is kind of interesting, is that as I was looking through here, there's actually no SPI section in the technical reference manual. And I asked Ivan about it, and he said it wasn't ready. So it'll be coming, but I thought that was pretty interesting. In the meantime, all I did was I pulled up I don't think I have it here, but I pulled up the ESP32 SPI. Ooh, this is the section I want. Yeah, so that was kind of interesting. DMA. So DMA is super handy because if you have a lot of data that you want to copy, and maybe not even immediately copy. So one place that we use DMA a lot in our other ports is for audio, where audio really is just a stream of numbers where the numbers indicate like the output voltage level. And audio itself is actually quite slow if you think about it. So like CD quality audio is 44.1 kilohertz, which means that 44,100 times a second, a value is copied and the voltage is adjusted on a pin. Now, that may seem like a lot, but for a computer, it's actually not that much because, for example, these chips I think are running, the ESP32-S2s run at 240 megahertz. So it's like a lot faster. So DMA can be really handy in that you usually can set up signaling between the destination and the DMA. So you can say like, I'm transmitting, an audio file that's a minute long, and you can set the DMA up that says, you can tell the DAC, the digital analog converter, like, hey, every 44.1 times a second. I mean, you would have a clock input, but say 44.1 times a second, update the number that's out. And then what it can say is like, oh, it can let the DMA know, be like, hey, I need another value, and then the DMA can copy it over, all without the CPU being a part of that, which is super cool. So DMA is really, really handy. And for displays as well, you can say like, throw all these bits out, spit them out on SPI to update like a display. So I was reading up a DMA. Welcome, Mr. Certainly. We're talking memory. One of the aspects of memory. Man, I don't know. This 2 hours might be a little bit tough because it's hot and I'm talking a lot. Let me take a water break again. All right, so different DMAs. Mr. Certainly says, I've forgotten mostly everything I've learned about memory. Well, we'll have a refresher. Drum. Nice. Man, we have so many punners in our Discord. It's great. So DMA can vary a lot from system. So this is where microcontrollers are really systems on a chip, right? Like the CPU is just one piece of the electrical machinery that's on the chip itself. And the system on the chip design kind of dictates what different DMA, typically you want to have like multiple DMA channels so that like you could have more than one thing being orchestrated by DMA at a time. So I was starting to look into DMA because it's really nice. It means that your CPU can do something else, and it typically also, because there's things like interrupts and that the CPU has to take care of, if the DMA is doing it, it can actually be more consistent as well. So it can actually speed up like large data transmissions because it doesn't need to worry about like all the other stuff the CPU has to worry about, which is really nice for displays. So trying to get my brain wrapped around how DMA works on the ESP32-S2. It has some caveats, which I think are totally reasonable. So this says peripherals with DMA support. So the UARTs, which I think I'm implicitly using by using the driver. SPI2, SPI3, I2S0, which I think is going to come into play a lot later. The ADC, so this is like sucking analog values in, right? Analog to digital converter. And then the copy DMA, which is actually able to just shuffle bits around within memory, which is going to be more and more useful. But we don't really use copy DMA much in the stuff that we've done. I think that I'm in the technical reference manual. So this is talking a little bit about the two different memory buses and the differences between them. I'm not going to talk about that. Okay, this is not what I want. There is a full chapter, I think, on DMA. Here we go. So chapter 7 of the technical reference manual is all about the DMA controller. Now, the question that I was thinking about is, how are they shared? Can all of those things be DMA'd at once? And also, what memories can they access? So if we look here, this is the list of modules and supported data types or data transfers, but it's also important to note that if the modules are on the same line, only one of them can be using it at a time. And if we look here also, it says for SPI3, which we're interested in, DMA can only be used to transfer between internal RAM and peripherals, which is some boards are going to just use the internal RAM. It's 320 kilobytes. But a lot of boards, like any of them that use I'm going to get this wrong. I can never remember. Is it the rover or the room module that has the RAM? One of the two modules has extra RAM that's external to the chip itself, and that SPI3 would not be able to access. And Unexpected Maker's Feather S2, which I have here on this desk, also has external RAM. But if SPI3 is used, DMA would not be able to access it as well, which means that basically like pretty often we're gonna have to like slurp stuff off with the CPU and then push it out. But then it also says for AES SHA, SPI2 and I2S0, R equals AM. So for SPI2, we can do DMA transfer from external RAM and the peripherals. Well, you all are confusing me. Rover has the external PS RAM. I thought the 1R and the 1M matched with the last letter of Rover and Room. I can never remember. I'm gonna have to implement this at some point, but not immediately. So yeah, and that kind of gets to my point, is that right now I really shouldn't care about this. It's something to think about in the longer term and kind of get stewing in my brain, like I was talking last week. But CircuitPython doesn't use external RAM now anyway, and it's kind of tricky on how we're going to do that, and maybe I'll go into this a bit. Anecdata says that's also true. So the 1R, the rover, has the extra RAM. Yeah, okay, I was right in that. Okay. CPU peripheral. Huh, interesting. So right now, all we use is internal RAM. So this is not an issue that I have to deal with right now. However, I went on a walk yesterday and I was thinking hard about this. I've talked with Jimmo from MicroPython about this as well, because they have a similar problem. Um, and the crux of it is that, do you share the external memory with the IDF or not? And if you do share external memory in the same way that you share internal memory, okay, Rover has RAM. If you share external memory, how do you split it up? And MicroPython is having some problems with the ESP32, which has the same amount of internal RAM as the S2 does, which is 320K, according to Jimmo. It's weird in that you have kind of two things doing dynamic memory, managing dynamic memory allocations. You have MicroPython or CircuitPython that knows how to manage its own memory. And in CircuitPython, we've added some stuff on top of what MicroPython does. And then you also have the ESP IDF that's living alongside MicroPython that's doing its memory management as well. And this has a couple challenges. One is a couple people have picked up. Yeah. Oh, Unexpected Maker's back. Yeah, if you have questions about this. So there's a couple challenges with having two different things managing memories at the same time. Oh, it has more. The ESP32 has 520K of internal RAM. Interesting. Yeah, and it's a big problem. Or it's a big problem that the S2 has even less. So, yeah, this is another topic that's doing in my brain that I'm not going to work on today. The thing that I do need to work on today, that I guess I could start, that I could also talk about, is that as we're doing SPI stuff, we're allocating memory in from both of those things, right? We're using the IDF to do allocations for like the interrupt, the lock, and the bus stuff on its own. And then we're storing those pointers in Python land, and we need some way to say, like, we need to free that. So if we don't free that stuff when we free the Python object that we're managing in CircuitPython, like, we're going to end up leaking memory forever, potentially, which is just going to be bad. So, like, if we leak memory in the IDF side of things, like, your Wi-Fi is going to stop working. You're going to start getting a lot of memory exceptions that you can't simply soft reset your way out of. Because a soft reset in CircuitPython will at least reset all of the memory that's managed by CircuitPython and MicroPython. So yeah, I've got to figure that part out. I've got to figure out how to manage memory that is allocated based on like MicroPython. Memory that is allocated by the IDF because of CircuitPython objects, and how to know when to free those. And one option that I need to look into more is there's a finalizer, which is like a function that is run as an object is deleted. We have two ways to handle it now that I have done. If we look here, we have this SPI reset. It's doing a SPI bus free, and this will free the memory that has been allocated. Yeah, this will free the memory that's been allocated and is still kind of living at the time that CircuitPython finishes, and it's not been never reset. And then in dinit, we also free the bus. Now, one thing I have to look into is if the bus is only one of three things that I'm having the IDF allocate on our behalf. The other two is the lock and the interrupt. And so I've got to figure out a way to make sure that those things are freed as well. One thing I could find is that the internal bus structures keep track of that and then free it on my behalf. I'll have to look at that. It's a pain. This is one of the pitches for those of you who like embedded development. This is the main pitch of Rust and why Rust is so popular, is that Rust is trying to kind of compete at the systems level of C, but what it has is notions for explicitly saying who's responsible for a piece of memory at any one time, which is very, very handy. And it also means that their compiler can do verification about like that you're following like the rules of memory management. So I want to look into Rust because memory management's really hard to get right, and having a compiler check it for you would be very, very nice. That's a long term thing. I'd love to have like Rust modules inside CircuitPython. That would be epic. They've done a lot of embedded work actually, which is interesting. So yeah, the immediate thing that I have to figure out is to make sure that my bus IO objects or the other IO objects don't leak memory, because that's memory that we lose for the rest of the life cycle of the device, not just the like soft reload. And so like imagine you're iterating on like bus IO SPI stuff, which means you're like starting and stopping CircuitPython, and we're just like leaking IDF memory every time. Like it'd just be bad. At some point you would never be able to allocate stuff again. So that's a problem I just realized in the last couple of days. And just means that I've got to be more particular, more careful for the work that I'm doing. And then, yeah. So Unexpected Maker says, yeah, RAM, CircuitPython, or like MicroPython versus the IDF is a tricky problem. No easy solutions, and something MicroPython has been trying to solve for a long time. But PSRAM support is super essential either way, but for another day. Yeah, so going back to the longer term, like, things to consider about memory is the IDF kind of lays it out two ways for you. With external RAM, you can basically like manage it yourself, or you can tell the IDF to like just manage it for you. And there's both good parts and bad parts for that. I think where I had landed was like, I'd just like to give the external RAM to Python and then only give the internal RAM to like privileged Python stuff, and so no heap allocation stuff, and then also the IDF, and basically let the IDF have all the internal RAM. Thinking about that is simpler, but it turns out that it's less of a solution if you're not wanting to support internal RAM well as well. So the current port, like the way that we do it for CircuitPython is we just have a 64K statically allocated array that is where our heap goes. But I've already had a couple people trying this port already, and they say, why does it only say I have like 64K free on the heap when I know it's a 320K device? So the way that the approach that MicroPython takes, according to Jim, who I talked yesterday about this and have been picking his brain. Yeah. So Jim is paid to work part-time on MicroPython by Damien, and has been doing some good work, and I can chat with him on Slack, so that's great. Jim has found yes, and Summersoft is talking about another thing, is that if we only used the external RAM for Python, what would happen to doing SPI DMA stuff? Would that mean that we could only use SPI 2? And the answer would be yes. One thing I was thinking about is having the ability of like, if you DMA a byte array, we could actually add a flag into the byte array object that says like, oh, we moved it, and actually put it in internal memory. Or we just change the logic here to say just like we always allocate SPI2 first. And then if we end up using SPI3 as a second bus, it just is slow because it can't do DMA. So yeah, that's another complication of this. Yeah. So going back to MicroPython and the ESP32, which Jim's done a lot of work with, they've had a lot of issues, I guess, with fragmentation. And the reason is that the way that they allocate their heap right now is like we just have this static 64K allocation. But basically what they do is when they create their heap, they ask FreeRTOS, the IDF, the OS that the IDF uses, okay, what's the biggest piece of memory, of continuous memory you have? And then they just slot in there. And that's interesting in that they get their biggest heap that they can support because the heap has to be continuous in the way that MicroPython does it right now, and CircuitPython does as well. But it means that like if there are large pieces of data that the IDF has to allocate later, it may not have any place to go next to that big chunk that CircuitPython's or MicroPython's grabbed. So they have a lot of issues, I think, with people just hitting like, oh, I can't do any more SSL connections because SSL has a big buffer to like decrypt stuff. And there is an issue. I was just looking yesterday at this because I'm like in that mode of like, I need to think this through more. Let me get all the information. There's been a couple pull requests and issues on MicroPython about making the IDF allocate within the MicroPython heap. So basically, like, it's a little weird in that FreeRTOS is not. Maybe I don't know that. The FreeRTOS allows you to do the allocations for it, and the IDF has a way it does allocations. Yeah, exactly. So Unexpected Maker says, yeah, but then IDF can run out of RAM for stuff like SSL. Yeah. Yep. So even if you had free space in that large chunk that MicroPython took, it can't be used for the SSL stuff, for example. So that's the conundrum, is that there really are like one memory region can either be administered by the IDF or it can be administered or maintained by MicroPython, and not really both. So there's been a couple issues / PRs on MicroPython about this. One idea was to say, let's let MicroPython manage all the memory and then hook up the IDF and FreeRTOS to use that. Yeah, I know it's delayed. That's okay. We're thinking the same thing. So yeah, so one technique would be to take all the IDF allocations and plop them alongside or inside or manage them with the MicroPython heap stuff. And then when I was talking with Jim, I kicked out the idea of, well, what if we did the reverse? What if we actually made MicroPython or CircuitPython allocations actually just call the FreeRTOS allocation stuff? Which could potentially work as well. Doing it that way has the challenge that like MicroPython and Python in general is very kind of like loosey-goosey or not explicit about when memory is created, and when it's created is pretty straightforward, but when it's freed is kind of much tougher. And you need some sort of data structure there to maintain, like, keeping track of all the things that still need to stick around, and then if they don't need to stick around, freeing it. So there is like some overhead that you have to manage as well. So Jim has this commit that was kind of like him running with this idea of using FreeRTOS to do the allocations for MicroPython. I don't think he got it working. He had some issues with alignment, I guess. But it's kind of like just sitting there, hasn't been merged in or anything. And so I was thinking, like, should I pick that up? Should I go that direction? The answer is I don't know. But it's something to think about. Yeah, so Unexpected Maker says, yeah, that seems like a smarter way. I think Jimmo liked it, but not sure anything has been tested. Yeah, I don't think it's hasn't been implemented. I think he hit some roadblocks, and it's just like not super important. Um, yeah, but he did send me a link to the commit yesterday, so I do have a his code that he did, um, which is like deleting a lot of GC stuff, which is weird too. Summersoft asks, would you just lower the GC trigger? I'm not sure. You should give me more context about that. No, Unexpected Maker is totally fine. I don't mind that it's delayed. And you'll hear this in about 3 minutes. I know it's delayed. I'm sorry. Internet problems. Um, yeah, so that's something I'm thinking about. And it's also something that's not important for the SPI stuff, right? Like, not leaking memory is important, but I can kick the can on like making use of all the memory down the road. And in fact, I think we're thinking, or at least I'm thinking, that like our next release will probably be 6.0 because we want to rename I squared C slave to something else. And we have that pull request for the master slave terminology that's going to prompt that. And the ESP32-S2 initial support seems kind of like a good place to say like 6x is all about ESP32-S2. And so I think what I'm thinking is that like so Summersoft says, well, let me finish my thought on 6x. So 6.0 would be the changes that we have currently. Basically, instead of 5.4, it would be 6. And then we would have the initial S2 support on there as well. We could add all the boards, but it would only have bus IO. It would be kind of slow, and it wouldn't support external memory. It'd be very basic. And then like 6.1 would be able to like we'd be able to iterate in the same way that we did with 5x. So like 6.1 would be like analog IO. 6.2 would be oh, we actually added external RAM support, that sort of thing. So yeah, I think that's kind of where we're gonna go. We'll talk about it on Monday, and this I should plug this. If you can handle 2 hours of me talking on Fridays, we have it's a worse time for Australians, but better time for Europe. Mondays at 11 a.m. Pacific, so 3 hours before my normal streaming time. 3 hours before my normal streaming time, we have a CircuitPython weekly meeting where we talk about all this stuff. So probably next week we'll talk about 6x plans. So if you want to follow that more, we have notes for that meeting as well, and it tends to be about an hour and a half. But it's not just me talking; other people are talking too. Okay, let me catch up on the chat. So that's my 6x thought. So Unexpected Maker says the GC has a massive cost, so triggering it early to always have more space really drops performance. Jimmo did a really great talk about GC and costs and options at the MicroPython meetup last year, which also is worth plugging. So the Melbourne MicroPython meetup happens every month, and Matt Trentini does videos of that on his YouTube page. Which are, yep, you can totally post them in Discord and I'll copy them over Unexpected Maker because I can post. Really, really good talks from like Damien and Jim and stuff. And that makes me kind of sad because I was actually planning on visiting Australia in August for PyCon Australia so I could meet these folks and talk about more of this stuff. But it's gone online and they're not letting people in Australia. And I don't want to travel right now anyway either. Yeah, maybe we should invite them to be involved in CircuitPython Day or something, which is right around that time. Let's think about that. That's a good idea. So yeah, Jim, Unexpected Maker continues to say, Jimmo did a really great talk about garbage collecting and costs and options at MicroPython meetup last year. There's a video on Matt Trentini's YouTube channel, definitely worth a watch, which I posted. And then Summersoft also says, would you just lower the GC trigger? Could be my misunderstanding creeping in. Doesn't the GC trigger collect a certain capacity or limits? That's an option. So the way that, popping off the stack a couple times, when you're allocating memory, it's pretty straightforward. You start where you last left off, basically, and you look through until you find a spot that's large enough. If you look through the whole extent of the heap, you're almost to the point where you're going to say you're out of memory. But there's one last thing you can do at that point, and that is to collect all your garbage, which is basically running the process of figuring out which memory you don't actually need anymore and freeing it. There's another way to do it that Summersoft is talking about where, like, if that location, I think, if that location that you start looking at is already past a particular point, then you'll run that collection process as well. And the benefit of having like a separate boundary is that you can potentially like reuse memory better and potentially have it more compact. I've got a couple of heap visualizations on my personal YouTube channel that's pretty interesting, and maybe it's worth a deep dive when we're into the external RAM, like kind of like a month or two from now when we're talking about this more. But I think this discussion about like using all of the RAM that's available is really going to be prompted by the network support, which I should have said as like 6.1, because network support is kind of like the second to next thing that I'm going to work on. So bus IO, a little bit of performance work broadly, because I regressed performance when I did low power, and I've got to fix that before we have a stable release. And then after that, like we'll release 6.0, and then 6.1 will be 6.1 will be Wi-Fi, hopefully. Yeah, so that's when we're going to need more RAM when we're doing all the Wi-Fi stuff, and this will come up again. Yeah, networking is kind of important on the ESPs. Yeah, there's some API work I want to do there as well. We've had some native networking APIs already, but I don't like them a lot because the challenge is that CPython doesn't really have the same model that we have, right? Like the model that we have in embedded world is that like there's really a separate chip usually that's giving us network access. It's not our OS that's doing it, that's managing it for us in the way that like Linux would manage it for us. So we've ended up kind of doing these like ESP32 coprocessors, the LoRa like cell network coprocessor. That model of like network is provided by someone else, and it's worked out really well. So I kind of want to like take that view of the world, refine it, and then apply it to native as well, so that the native stuff just provides something that looks like a coprocessor. It's not like any more fundamental than that. So we'll get there. I gotta stop talking. But yeah, it's all really good discussion. Memory management's really hard, and it's also important to not get too distracted. As I get distracted, we'll focus on getting bus IO out the door before we worry about it too much. Unexpected Maker says, "Gotta run. Sorry, no worries. Thanks again for doing such a cool deep dive. Love how candid you are." Yeah, I love working on open source because I can be very open about it. It's great. Like I worked at Google, and I was like, I can't tell you what I'm working on, but I can tell you I can stream what I'm working on here, which is awesome. Okay, we've got 30 minutes or so. We talked all about memory, which is good. You can see here, I'm just going back for those of you watching. I'm going to keep going through the file that we've got, that I've gotten sketched out. So this SPI HAL context struct is something that the IDF actually usually maintains internally, so the structure of the IDF is there's like this driver component that uses the HAL layer, and the HAL layer is like supposed to be agnostic to the RTOS stuff. So I'm circumventing all the driver device level stuff by going directly to the HAL myself. And the way that the HAL works is basically there's this like context is not a bad example or a bad name for it because it's like kind of like where everything is just thrown in. So there's top level like so HW is like the pointer to the actual like place in the memory map where the SPI device you're using is mapped, and then these are like DMA descriptors, which are like allocations that you pass to it, and then the number of allocations, and then more timing information, and the timing information then kind of applies at like a per transaction level, and then lastly, or yeah, and then there's this command address dummy sorts of stuff that is like even more per transaction stuff. So like all of the HAL APIs kind of just like take this context and use the bits that it cares about, which is fine. It's not meant to be a public API. Like there's literally like a README that says like don't use this, or like this will change without notice, which is fair. But it's the level that I need in order to implement kind of like at any time we can just call configure. So yeah, that's what this struct is. I've done a lot, like I said, I've been just doing a lot of digging into the HAL, into the IDF in general. So let's keep going. SPI never reset just sets the array for not resetting, and the pins as well, making sure they don't get reset. We track whether an object is deinitialized, because Python doesn't have a great way to, let's say, like really like delete this thing right now. For all of our SPI or for our hardware APIs, we provide deinit as a way to say like, no, really, I'm done with it. And then we have this deinitted thing that is a check that shared bindings will do, just like it'll throw an error if you try to use it after it's deinitted. And that allows us to like free up memory and pins and stuff, kind of before Python's actually gotten rid of the real object. It just makes it more concrete. So when you deinit, if you deinit explicitly, we actually turn off the never reset, because if you want something to live past the end of something, you shouldn't deinit it. So that's a way you can actually undo never reset, is with an explicit deinit. We free the IDF memory and then we reset the pins, which may actually reset the pins. I'm not sure. So the next function we have is configure, and configure is kind of like the whole reason we have this problem. One of the reasons we have this problem, and that like only at the HAL level can we just tell the device like reconfigure yourself for this clock speed and polarity and stuff. So first thing we do is we just see if we're already in the current state. And the reason that you do that is it can be kind of costly to reconfigure stuff. And it can also be pretty common that like you only have one thing on the bus and it has all the same settings every time. So it's good to make configure quick if you're not actually changing anything. And then we hold on to the arguments there. And it's kind of interesting to note that we do have both target frequency and a real frequency. And the contract that we have in the SPI API is that you give it what kind of your maximum is, what your goal frequency is, and then we'll pick as high as we can underneath that, because it's complicated how you actually get the frequency out that you want. And the reason is that like there's clock trees of like the CPU is running at this speed and you want to divide that by 4, and then like, oh, you can divide that thing that was divided by 4 by another different factor, and like you're never gonna, like in only certain cases can you get exactly what it is. So it is possible that real frequency is the same as target frequency, but it's not guaranteed. So we track both, and we do that sanity check or the early exit based on target frequency, so that if we end up with a different real frequency, we don't always reconfigure just to find out that we're actually where we want. KDAR, I hope I said that right. It says, just a quick question. Will this talk be available afterwards as a video to watch? Really sorry for this question. Yeah, all of my streams, my deep dive streams are on youtube.com/Adafruit as a like just a rebroadcast or a recording of the whole stream. And there's a playlist called Deep Dives with Scott, I think, that I add them to. So you can go back and watch all of them. Yep. Cool. So yeah, configure is the reason that we made this kind of are in this mess in the first place, because like the driver level, the device driver level of the IDF wants to manage this all for us. This is the lock stuff. So this is actually like trying to use a proper FreeRTOS lock to track the locking of the device. I think it's right. We'll see. One subtlety here is that usually with Trilock, if you can't get it immediately, you return. But real-time operating systems tend to be designed so that if I'm waiting on a lock, you can like basically stop running that task and let other things run, which, you know, the thing that holding the lock should be that thing, and then switch back to the thing that's waiting on the lock when the lock is free. So this may actually work a little bit differently, and we'll have to see how that works. For write and read, right now I'm just delegating to transfer. I'm ignoring this write value thing, which could be a problem, but I couldn't find, because the technical reference doesn't have it, I couldn't actually find the state of, so SPI is two directional data lines, right? Like one is out from the host and one is in from the device that's selected. And so if you're only reading, if you're only paying attention to what's coming from the device, you're still transmitting something to it. And some of those things actually care. And so we have this write value, which is the value that you're going that way. Kedar says, thank you for your answer. Now I can sleep as it's really late here. Thanks for hanging in there. And yeah, you can either drop a comment if you have questions in the video or go to our Discord, adafru.it/Discord, and ask questions there. We'd be happy to answer them. Cool. Thanks for watching. All right. So read and write, I'm just delegating to transfer, and I'm ignoring write value. And I kind of just cribbed this from the way that the driver works. So we have to fill out the bit length. So it's interesting that it's tracking bit length in terms of, actually I need to change this too. I think it's bits. So the thing is that SPI can actually have different like word lengths. So you can have like 9-bit SPI where every byte is like 9 bits and not 8, which is weird. And I don't know of anything that does it. But I think I do have it set up to do that. It gets very weird because like then your send and receive buffers are like, you know, however many like 8-bit bytes it takes to fill. Yeah, it's a pain. But yeah, I think that's right. And somebody can correct me if my thought on that is wrong too. And again, I haven't actually compiled this yet. I was hoping to do that today. Maybe that's what I can do is like just start to hunt down some compiler errors. There's certainly some. It's probably mostly includes. Anyway, I think we've had an episode that was me fixing compiler errors already. That's really fun. Okay, so we set up the transaction, which is like getting the hardware in the right state. Preparing data, I think, is a lot of like prepping all the DMA stuff if you're using DMA. And then just clicking start. And the HAL itself is not asynchronous in any way or anything. Well, it is asynchronous, but you basically only know it's done. Like start really just starts. You don't know it's done. Ooh, Mark is on a tear, just routing another board. A 1-inch square board. Yeah, routing's fun. Maybe I want to make a V3 of the Sala feather adapter because I want to put the reset circuitry on it. Oh, and heads up, I know the Unexpected Maker is not on anymore, but if you do watch this, caveat on the pin that you pick for the reset is that you should make sure that it has no default pull. Some of the pins, like the SPI 0, SPI 1 pins, have a default pull, and that can mess up the like 1-bit memory. Okay, so this is the other thing that I haven't done yet, but I can talk about it. Maybe it's the last thing I'll talk about today because I've been talking a lot and my voice is getting tired. These are really easy. These are just like returning the data. So transfer is where it's at. And it turns out that the SPI device has a buffer. So in like SAMD 51, I think it's like a word. So like 32 bits. For my testing, I'm using GPIO 16. The reason I bring it up is because TAC was trying it on 26 and it didn't work. And he also had to bump his resistor from 100K to a meg. I'm using a 1 microfarad capacitor and a 100K resistor, but TAC had to use a 1 microfarad capacitor with a 100 mega ohm resistor, and both of those should work fine. So I would skew higher on the resistor. Basically, you just need to hold the like high charge long enough to read it on the second time. The resistor's there only really because ideally you want that to always start at 0 when you like plug it in. Okay. So there's a buffer in the SPI peripheral. It is, and the reason I found it is like you can actually dig into the IDF enough to see like register, like structure, like structs that are defined to mimic the registers, and those are in like SPI types is pretty low level. LL is obviously low level. And then where is it? It's in SOC include. No. SOC. ESP32-S2 include SOC. SPI struct. So this is a structure that mimics like mirrors the actual memory layout of the peripheral that you're like writing to. So there's this data buff. I think that's what it's called. Yeah. So there's this data buff element, which is actually like a memory buffer that the device itself has. It is 18 uint32s long, which is 72 bytes. And that's super handy because that means that you can just write all that data straight to the SPI device. You don't need to use DMA if your transaction is that short, which I think outside of displays, it probably is, which is another wrinkle. Talking with Summersoft about like, do we default, like, do we always pick SPI 2 or do we pick SPI 3? Like how likely or how confident are we that we'll actually use the DMA? And it went past my mind of like, could we actually potentially swap? So like pick SPI 3, but if we need to do DMA and SPI 2 is free, maybe we can actually switch them in, which is not that crazy of an idea. Right, because if we're going through the GPIO matrix, like we have that flexibility, which is interesting. Okay. So that's a good boundary. And I think basically if we have a long transfer, then we want to rely on like interrupts to tell us when we're done so that we can basically let other things happen while that's going on. And if we're short enough, and in this in this example, I think I'm going to define short enough as like right to the buffer of, if it fits in the buffer of the SPI device, then we can just use it. Although I have this and false here because there's nothing in here. So that's why I had this note to say like set the interrupt and wait on the lock. Otherwise, what we can do is we can call this it's whether the user transaction is done or not. And then we can run background tasks while we do that. Whew. And then I think here we actually want to return true because we're not doing any sort of error checking. It should return true if the transfer happens. So that's through the end of the file. I said I was going to run through stuff, but I'm kind of hot and tired of talking. So I shouldn't have said that, but are there any other questions? Otherwise, I think I'll just call it a little early. I'll go for a walk, cool down, and get the room cool, and then I'll jump back and do some work on it after that. Any thoughts? I know it's kind of delayed, so I'll just stand here and drink my water. I'm gonna go buy some ice cream. That's what I'm gonna do. Actually, I need to make a grocery list, I think. Abominable says 5 seconds on Snack. I don't know much about Snack. Do you have questions about it? Or I met Keith. So, so Snack, we just created a channel for it on Adafruit because they asked me to, so I did. Snack is a project by Keith Packard, who's been very involved in Linux and displays for a long, long time, and also teaches programming to a lot of folks. It is a Python-inspired language designed for really small micros, like 8-bit AVR level stuff, which is funny because I saw him calling CircuitPython a MicroPython, like medium-sized Python, which I thought was funny. Which I guess is true because he's operating on smaller stuff. He does some interesting memory stuff as well that we talked about. So I was down in Portland for Pi Cascades in February. You've seen the pink shirt. That's what it's from. And I had dinner with Keith, which was awesome. And I appreciate him taking the time to do that. It's his Python-inspired language for really small micros, designed to be simple enough and easy enough to teach. I just looked a little bit, and it looks like there are some trade-offs that I would not make in terms of like it being Python. I don't remember what those are, so I could be totally wrong. But I think teaching languages are good, and embedded is a great way to teach. So I'm all for it. But I haven't looked into it a lot. The one memory thing that I was talking with Keith about was, I'm gonna bring this topic up again, but it's good. So we talked about this, the issue of memory fragmentation, and memory fragmentation is usually handled, I think usually is a safe word to say, but in more complicated like garbage collection or memory management schemes like Java, they had the benefit of being able to actually move memory, which allows you to say like, when we collect, take everything that's still alive and like compact it so that the region that we're left with is like one giant free region instead. MicroPython and CircuitPython can't do that because we don't know where all the pointers are. What we do when we want to say like, oh, we're going to keep this around is just like, this number could be a pointer. We don't know it's a pointer for sure. And because we think it could be a pointer, we'll keep it around. What Sneck does, and I haven't looked into the details of this, but what Keith was telling me is that he knows a way to know, he knows what everything is a pointer. And so what that means is that when he decides to do like a compaction, he just looks through all the memory and rewrites all the pointers to move something, um, which is awesome. And I wish we could do that as well. But that's, I think the more traditional way that that's implemented is that you have like another table of memory that you use as an indirection, which is again cost memory and may not be super beneficial. So yeah, it's an interesting project. SNEC is an interesting project, and if you have more insights from it, let me know. I totally just got that, Mark. Cat food for Spook. I don't have to get cat food until next week. But yeah, I was gonna get milk actually too. All right, so that's my more than 5 seconds on SNEC for Abominable. Anecdata is typing. Otherwise, are there any other questions? I'm trying to remember everything I was gonna get. I was gonna get milk. I was gonna get ice cream because we have strawberries and raspberries to eat. And then pickles I was gonna get. I feel like there's one other thing I was gonna get and I don't remember. Maybe I'll remember it. Anecdata says, any thoughts yet about the distant future, whether IDF Wi-Fi networking low-level APIs will be exposed to CircuitPython? I don't know what you mean by low-level. I think that the level I'm shooting for is like socket, like CPython socket level, which I think we kind of have in our current like coprocessor networking stuff. I think that one thing I've seen with the current coprocessor networking stuff is that it's kind of like not very strictly separated between like managing the connection to the coprocessor and actually like providing a socket interface. So one thing I'd like to do is make sockets more strictly CPython socket like, in the way that like Adafruit requests in the future should be able to be given like a CPython socket and work and be tested and be fine. So like anything that's built on our networking libraries should work with CPython socket just fine as well, would be my goal. And that's nice because then if somebody moves to Blink on Raspberry Pi, they can still use all of our networking libraries, even if like Adafruit requests, like there's real requests, and that's certainly more full featured. But like you shouldn't have to move to regular requests just to move your CircuitPython code into Blinka. So yeah, I don't know exactly what you mean by low-level APIs, but I'd like to unify our networking APIs at a level that allows us to do a lot of different protocols. And that would be at the socket level, I think. The CPython socket level. Anecdata is typing, and I'm drinking water. I'm trying to remember what the fourth thing I was going to get. Oh, I was going to get flour. That's what it was. My wife went to visit her family for the next 3 weeks. So I'm, as the person at the grocery store yesterday said, it was independent study. So I'm thinking I'm going to make pizza and maybe some more other things. So I was going to get more flour because we've been making stuff. I actually just made like a flatbread as well. Cool. All right. Anecdata says I'll try to formulate more on the question later, for later. Thanks. Yeah, you know how to get a hold of me. Let me wrap up. As folks know, or I will tell you again, I will reiterate, naan pizza. So I tried to make naan. That was one of the things I made. Okay. Changing channels, monitoring mode, low level, stuff like that. Actually, that reminds me of another thing. The way that we do custom like per port APIs is we introduce a module specifically to that port. And I was actually thinking it would be nice to have a port-specific module for the S2 where we can expose some metrics about the IDF's maintained memory, so that we can both do like GC mem free for CircuitPython and like free size or whatever for the IDF. So I was thinking about adding an IDF. Module that we could also do like IDF dot component name dot whatever as a way to do it. Yeah, so Mr. Certainly, I made naan. It didn't work out that well. I don't think I used enough yeast, and I left it in the fridge too long. But I also made just like a super simple yogurt flatbread that turned out really good, and it was like super quick because it had no yeast. It was just baking powder. But yeah, wait, is this an electronics stream? I don't know. Yeah. Okay, so let me stop talking about baking. If you want to get a hold of me, you can go to adafru.it/discord. That will get you into the Adafruit Discord server, and you'll be able to chat with me. You'll be able to chat with a bunch of other folks all about the ESP32-S2 and electronics and code and all of that stuff. We have an off-topic channel if you want to talk about baking, or Age of Empires 2, which I've been playing a lot of. If you want, maybe I'll look at and try to get this delay things sorted out. I'm sorry about that. I typically stream Fridays at 2 p.m., but this week I adjusted it because tomorrow is Juneteenth, which is a celebration of the freeing of the last slaves in the Confederacy in the U.S. And I think that's important, and I just learned about it, so I want to recognize that. I'll probably work on some election cal stuff this weekend if you're curious. And I feel like there was something else I was going to say. But yeah, I'm going to continue streaming for the foreseeable future. Obviously, we've been talking a lot about we've been talking a lot about like all the extra stuff or the additional stuff to do for CircuitPython and the ESP32-S2. And yeah, thank you all for hanging out. I'm just going to talk about baking a little bit more and cooking, because Summersoft asks, how are you on sauces? That's a good time-consuming skill to dive into. I stopped at a very serviceable hollandaise. Yeah, not good at sauces. Although I do gardening. We have some raised beds, and I grow tomatoes, like cherry tomatoes, and I made like not a sauce, but like just a cherry tomato like mushed in a pan sort of thing that was good. It'd probably be good as like a pizza sauce too. I also there's a local business here that makes a bunch of mustards, and so I ordered a bunch of that, some of that for Father's Day. I'm gonna go visit my parents on Father's Day and give them that. Bruce has been tinkering around with maple whole grain mustard, which has got me thinking about that. And then Zach has this funny comment of Scott the unexpected baker, which I definitely laughed at when I first saw it too. Anecdata says, awesome deep dive, very interesting to get in the architectural constraints and design trade-offs. Awesome. Well, I think we succeeded at having a deep dive this week. I hope it was all as helpful for you all as it was for Anecdata and myself. Obviously, it's still early days and a lot to think about. So if you have suggestions, opinions, want to get more involved, join our Discord. This video will go up on youtube.com/Adafruit. And yeah, thank you all for hanging out. Have a great weekend.